In this video, we'll be talking about inheritance. This is a relationship we can set up between two classes. When one class is derived from another class, we call that other class the base class. A derived class inherits all of the member functions and variables from its base class. This means that the derived class has those members without having to declare them itself. This is a super useful tool for extracting shared code from multiple classes into a common base class. Let's dive in and see what this looks like in C++. We'll start with two classes named base and derived. To make derived inherit from base, we need to add a base specifier list. After our class name, we add a colon, public, and the name of our base class. This tells us that derived inherits from base. Any member that base has, derived has too. So we can create an object of the derived type, and we'll be able to ask it for the B member that we declared in base. Similarly, we can call either func1 or func2 on our D object. Now we've got a way to isolate shared member variables and functions from multiple classes. Sometimes our base class implements some behavior that we need to change slightly for our derived class. Let's say our base class has a printAll function that prints the names and values of all of its members. That works great for base, but when we call it on our instance of derived, we'd want it to include derived's members too. We can do this by having derived override the printAll function it inherited. Before we can override this function, base needs to tell the compiler that it can be overridden. We do this by marking the function virtual. Now the compiler knows that classes inheriting from base might replace this function with their own version. And we can do exactly that in the derived class by adding its own printAll function and using the override keyword. This override keyword tells the compiler that this function is meant to replace a function from our base class. If that function doesn't exist in the base class or isn't virtual, our code will fail to compile. Now our call to printAll runs derived's version and shows us all of the variables. A quick aside here to note that the override keyword was added in C++ 11. It's not strictly necessary to use it, and you'll see old code that doesn't have it. You can override functions without using the override keyword, but if you make a mistake that causes your function to be a totally new function instead of an override, the compiler won't catch it for you. This can be as simple as a typo in the function name, so it's a good idea to always use the override keyword in your code when you're trying to create an override function. Now we've got a version of printAll that covers all of our variables, but we've had to duplicate code. If any of the variables in base change, our override implementation has to be updated to reflect that. It'd be nice for a function like this if we could run the base class's version of the code and then add our own steps after. But if we just try to call printAll, we'd still be calling derived's version. We need to somehow specify that we want to call base's version of the function. We can do that by using the class name as a namespace qualifier for our function call. This is now specifically calling the base version of this function. And now we'll still get all of our variables printed out, but derived has only had to handle the variables that it added. Okay, but what happens when we start adding constructors to our classes? Well, let's add a constructor to base that takes in two ints to initialize A and B. Now we get a compilation error when we create our instance of derived in main. It's telling us that the default no-argument constructor for derived has been deleted because base doesn't have a no-argument constructor. When we construct an object, its base object has to be constructed too, so we have to play nicely with our base class constructors. Let's add our own no-argument constructor to derived that calls the base constructor with some hard-coded values. We can call our base class constructor by adding it as the first element in our member initializer list. Again, that list starts with a colon after the constructor parameters. Then we have the base class name and the arguments we'd like to pass to its constructor. Adding this constructor to derived has solved our errors, and we're back to printing out all of our values. When we introduced classes, we talked about controlling access to our members with the public and private keywords. There's a third access level that becomes relevant with inheritance called protected. Protected members are available in the current class code and any derived classes. If we add a protected member variable to our base class, we can access and manipulate that variable in our derived class without issue. But if we try to print that variable out in our main method, we get an error letting us know that that variable isn't accessible in this context because it's marked protected. So now we've seen all three access levels. Private members are only available to the class that declares them. Protected members add availability to classes that inherit from the declaring class. And public members are available to everyone. Now you might be looking back at the code that made derived inherit from base and notice that we used the public keyword there. This is, in fact, the same kind of public. When we inherit members from a class, we don't have to inherit their access levels. We can put a cap on how public our inheritance is. When we inherit publicly, all inherited members retain their original access level, and other classes can know that we're derived from the base class. When we inherit with protected, all public members from the base class get bumped down to protected in our derived class. Additionally, only code in our derived class, or classes that inherit from it, can use the knowledge that we are inheriting from the base class. Finally, when we inherit with the private keyword, all inherited members get bumped down to private members in the derived class, and no one outside of the derived class knows that we're inheriting from that base. This doesn't come up often, as most classes inherit publicly, but you already know now what public, protected, and private mean, so we've got no reason to handwave past this use of those keywords. There's one more thing I want to note before we close this chapter on inheritance. If you have a base class with a destructor, you should basically always mark that destructor as virtual. If you don't, you can get into situations where an object is destroyed, but the derived class's destructor is never called. This is usually bad, since destructors clean up resources, so you're likely to start leaking something, like memory or file handles. It's an easy rule of thumb though. Whenever you make a class that you intend to derive other classes from, make sure its destructor is virtual. That's all for this video. We've covered how to derive one class from another, how to override functions inherited from a base class, how to handle constructors in derived classes, and the protected access level. I know this is a lot, and if you haven't dealt with inheritance before in another language, know that there's a lot more that can be done with these concepts. What we've introduced today is just the fundamental mechanics and syntax of inheritance. This level of understanding, though, should be enough to wrap our heads around the ROS code we'll be writing that uses inheritance.